I hope everyone's doing well today. For this video, I am Mr. Ish. Thank you for joining me. It's a very interesting one here, and it's slightly out of the ordinary because it's a chemistry video, but you will see it's primarily all algebra. And that's usually the case when it comes to many of these more out of the ordinary chemistry problems. We have to analyze particular data here and come up with the items which will fill this last row of this table. But what is it we have? We have a reaction. Two atoms of hydrogen are combining to give you a diatomic hydrogen. Everything is in terms of gas. You have atoms combining to give molecule. And what we're seeing over here, we have a row here of your millimeters mercury total pressure of the system. We have time here in seconds, and then this is the item we have to find. We always have to find the remaining partial pressure of your reactant here, H, your atomic hydrogen, at a particular point in time. That's what we have to find. We have to find the partial pressure of your atomic hydrogen which remains at each of these time intervals. Now look, when you're looking at the pressure row, the pressure is decreasing over a time. Why is the pressure decreasing? Because if you think about this equation PV equals nRT, and you focus on the pressure and the moles, you know pressure is always proportional to the moles. As the mole increases, the pressure increases. But you know this also represents number of particles, number of atoms, number of molecules, all of that. And obviously I said particles. But if you're increasing the number of atoms or molecules or particles over time, then obviously the pressure will increase. But if you're decreasing these items, then the pressure must decrease. Here you're seeing two atoms every time are combining to give you only one of these. You're seeing a decrease here in the stoichiometric coefficient. If you have a lot of these and over a period of time they combine, you'll obviously have fewer number of particles in your reaction vessel, so the pressure must decrease over a time. Given all of that, now how can we utilize total pressure to determine the remaining partial pressure of your reactant which exists at each of these time intervals? You will see it's algebra primarily. Start by classifying what your variables are. You have here a partial pressure of your reactant, atomic hydrogen, which is initial, and you know what it can be. Technically, it can be exactly what was the total pressure at the start of your system, because at the start of the reaction there was only reactants, there was never any product. So what we can do is label this, and this will be our one item we can use. At the start of the reaction, the partial pressure of your atomic hydrogen will be 500, but I'm just erasing this part because I'm only classifying variables over here. Another variable I can do is find the partial pressure of your product, which is your diatomic or your molecular hydrogen at an initial time period, and you know what that would have been, 0, because at the start of the reaction there was no product, so obviously it's equal to 0. But again, we're only classifying the variable, so these are two variables. What happens over a period of time? This thing decreases, your reactants decrease by a certain amount and your products increase by a certain amount, and what is that amount? We'll call that X. Your partial pressure of your reactant at a given time is always equal to what was initially present minus X. Your partial pressure of your product, your molecular product or your diatomic product at a given time is always equal to what? It's equal to the amount of the reactant decreased by over 2. Why am I doing over 2? Because look at the coefficients, 2 to 1. 2 of these give you 1 of that, over 2. The total pressure of your system at a given time is equal to the partial pressure of your atomic reactant plus your partial pressure of your diatomic reactant at a given time. See, at a given time. And what is that? Well, I have these values. I have P, H, and I minus X plus X over 2. What is this equal to? Simplify this. You're having PHI. I'm saying PHI, but you know that's partial pressure, that's your atomic hydrogen, and that's your initial amount, minus X over 2. That's what it is equal to. This right here is equal to this. But now using this expression, I can actually solve for X. If I push this on the other side, I push 2 on the other side, and I solve for X and push the minus on the other side, you can do this in your head. You'll have 2 times. The minus will flip things around. You'll have partial pressure of your hydrogen initially minus total pressure of your system at a given period of time is equal to X. That's exactly what it is. Now look here at this particular equation and you solve for X and bring it in. And that's exactly what we'll do. Your partial pressure of your reactant at a given time, which is what we're always calculating, the remaining partial pressure of your reactant at a particular period of time, will be equal to PHI minus X, which is all of that, 2, I'll open it up, PHI minus 2 total pressure at given period of time. But you can simplify this. We'll clean it out and we'll solve it. Minus times minus is a positive. We'll have 2 times total pressure at a given time of your system. phi minus 2 phi will be minus phi. That's the equation which will help me give the items which I need for this block. And it'll always be giving me my partial pressure of your atomic reactant at a given period of time, which represents how much remains at a given period of time. And this is the equation. I already know right here, initially this thing was equal to 500. Now let's look at the first item. At time 0, the only thing which existed was reactant. There was no product. So the total pressure at that time is equal to everything coming from the reactants and nothing from the products. We have 2 times the total pressure at that time is 500 minus phi, but I already know at the start of the experiment the initial value is always 500 minus 500. I'm getting here a value 500, and it's all in millimeters mercury. It'll be 500. This item over here will always be 500 because that was what the initial amount was. The initial total pressure of the system was entirely from the reactants, and it was 500. Now let's do the next column. We'll do 2 times the total pressure at that particular time, which is 450. 2 times 450 minus obviously the 500. I'm getting here 400, and that'll be the remaining amount, 400. Now let's do the next time interval. It'll be 2 times the total pressure at that time, 391, minus obviously this 500, which value never changes, 282. That's what we have. Let's do the next one. It'll be 2 times the total pressure at that time is 345 minus 500, 190. And last item, we'll do 2 times 299, the total pressure at that time minus obviously the original 500 in terms of the partial pressure of your reactant is equal to 98. So that's everything you have over here, and it should be right. You're seeing over a period of time the total pressure is decreasing. Obviously it is. Look at these coefficients. You have more reactants and fewer products. As the number of atoms or molecules or particles decreases, the total pressure decreases. Obviously for the reactant the partial pressure is decreasing with time, and everything should be right over here. You can see it was primarily all algebra disguised in the form of a chemistry question. Thank you. Have a good day.